Hello everyone, we are Team 5 and we would like to start our final presentation for our term project, which is to replicate and make improvements upon a 2020 NURBS paper called Model-Based Reinforcement Learning for Semi-Markov Decision Processes with Neural ODEs. I'll be giving you a brief recap of the paper and related works for our project. After that, Jinwon will talk you through the replication and improvement process, contribution, improvement approach, and methodology. Then, Minchell will talk about results, evaluation, and discussions. Deep reinforcement learning has led to major advances in various applications. However, most of the deep RL algorithms formulate a problem in discrete time steps, but many real-world sequential decision-making problems act in continuous time. For example, control problems are generally governed by systems of differential equations. Most previous work on continuous time RL is built on series of semi-Markov decision process, or SMDPs, whereas all of them are model-free methods and use simple linear approximators. This paper's main contribution is an elegant solution for modeling continuous time dynamics and building a new model-based RL framework for SMDPs. Neural ODE is a new family of neural network architectures first introduced in NURBS 2018 best paper. The setting is that there is a vector-valued latent state z. This state changes continuously with respect to time, and the function f defines the derivative dzt dt. We can make one simple change to make residual networks continuously defined with depth, like in ordinary differential equations. By replacing y equals fx with y equals z of t, we can feed the current depth to the ResNet block and use a fixed set of parameters for the entire depth. This change means that the dynamics are now defined even between layers and can change continuously with depth. This model then now defines an ordinary differential equations. We can always replace primitive Euler's method with a more sophisticated adaptive ODE solver. We call this model an ODE net. To train these models, we somehow have to get the gradient of the objective through the ODE solution. A naive way would be to simply backpropagate through the operations of the ODE solver, but this is a bad idea for two reasons. First, because storing the intermediate operations of the solver adds high memory costs, and second, this approach adds the numerical error to the gradients. More generally, we should always try to approximate the exact derivative and not to differentiate the approximation. Therefore, we take the exact derivative through the adjoint sensitivity analysis. Since we are tackling on a continuous time dynamics, we need a slight modification from classical Markov decision process. A semi-Markov decision process is a tuple SAPRT gamma. The major difference compared to the Markov decision process is that instead of a discrete time steps, we assume that the environment has transition dynamics unknown to the agent, where tau is a continuous time variable between the taking action A in observed state S and arriving in the next state S and can take the new action. For the main method, authors decompose transition dynamics into two parts, one to predict interval timing and one to predict next state. They used an encoder-decoder based RNN with neural ODE called latent ODE to model the transition dynamics to predict next latent state z prime. To train the model, we use overall objective, which is the weighted sum of loss for prediction of state transition and loss for prediction of interval timings. We use DDPG and Q-learning to optimize the policy and model predictive control for planning. One of the key models in our paper is the latent ODE, which is introduced in a paper called Latent ODEs for Irregularly Sampled Time Series. In this paper, the authors first proposed ODE-RNN, a neural ODE and RNN hybrid with continuous time hidden dynamics. Then they applied their ODE-RNN to the latent ODE, a encoder-decoder model first introduced in the neural ODE paper in order to more effectively parameterize when data points are irregularly sampled. The encoder is constituted of ODE-RNN that approximates the posterior of latent state, and decoder is defined by an ODE net whose initial latent state Z0 determines the entire trajectory. Encoder and decoder of latent ODE is then jointly trained by maximizing the elbow. A team from Google AI tackled a similar robot manipulation task of ours, where they made an Euro 5 robot to pick up and throw an arbitrary object into a target basket. The key takeaway is that they use something called residual physics, where the release velocity is determined by a hybrid of physics-based controller and a data-driven residual physics delta. The residual physics is added in order to compensate for object-centric properties and dynamics such as center of gravity and moment of inertia. They show that without any reinforcement learning, the residual physics model outperforms physics-only or regression-only models. OpenAI released an article called Hindsight Experience Replay that deals with the well-known challenge of sparse reward in reinforcement learning. The main idea is to learn from failure by re-examining failed trajectory with a new virtual goal set as the final state of the trajectory st. The failed trajectory is added and replayed in the experience replay buffer with the virtual goal specified as st instead of the actual goal. They demonstrated its performance on our task along with some other robot arm manipulation tasks and showed that in sparse reward settings, DDPG plus HAR well outperforms DDPG, which by itself almost fails to learn anything.
The author provided the open source code, so we can easily change what we want. We implemented prior work first on 3 OpenAI and 3 Bujoko scenes. After verifying them, we scaled up to complex manipulator works. They experiment in a low dimension like a swimmer, so verifying scalability is an important issue. To verify that issue, we come up with an experiment's complex environment which is fetch slide free 0. This is the task of learning how to hit the hockey puck and slide it into the target. We'll see if ODE network can learn the dynamics or not. First, we configure the robot environment for learning fetch robot. The baseline code was the raw dimensional simple environment such as a swimmer and hopper provided by the Mujoko. We reconfigured the environment to verify that your ODE works well even in a high level and complex environments. Based on the FetchSlide robot published by OpenAI Gym, we created a task in which the robot hit the puck to reach the goal. As a component of the environment, the robot has 31 states such as the joint angle and link position, and the action is the end effector position and a distance to go to the goal. We also defined the reward to fit the robot's new task. Previously, if the distance between the puck and the goal is in the threshold, a reward was received. We call it a sparse reward. We penalize the agent proportionally to the distance between hockey puck and the goal to give the more dense reward. We call it dense. And the modified reward is when the puck exceeds a goal position, the penalty grows exponentially via the gap. Lastly, a collision penalty occurs when the puck collides with the side of the desk. We wanted to diversify our test and train scene to suit our newly defined task. We construct a simpler 2D environment with diverse and dynamic constraints. As shown in the figure on the right, the robot starts learning incrementally from the easiest task at the top to the most challenging task at the bottom. This will allow the robot to generalize and perform complex tasks well in various environments.
Here is our quantitative result of our model-free architecture by reward shaping and method against incremental scenario on the previous page. First, when the robot moves along the x-axis, which is the simplest scenario, she showed that the average success rate of the robot was high when it is implemented on the dense reward. And it showed that the worst performance in the modified reward. The next typical scenario, when the robot can move in the 2 dimensions on the x and y axis, show the best performance when using the modified reward. Also, as shown in the running graph on the right, as the running progresses, it can be confirmed that the running is working normally through the convergence of the rewards. In the first scenario reported earlier, the robot can only move the x-axis. When the dense reward was used, the best performance was shown. And here, the robot can hit the puck very well to the goal positions. The following is a video reporting on the robot's behavior and trajectory when using the modified wheel shape with the moving X and the Y axis, which is shown the best result in a high-dimensional robot that can move in the X and Y free axis. Our last task was to move the frog to a goal that was randomly generated every episode with a robot that could move freely in the X and Y axis. Because it was the highest difficult level of problem, even with our proposed method and reward was implemented, but the board showed the limitation that it could not run properly. This appeared to be an area that needs to be improved in the future. The following are future studies to be improved while carrying out this project. First, it is necessary for the robot to run more diverse environment for generalities. Various physical variables need to be taken into account, such as randomly sampled goals that performed poorly in the previous task, or situation in which the power collided with the wall. We can also think about running a scenario where two or more robots exchange power with each other instead of one single robot. The second one is the execution speed calculation of the neural ODE improvement. The current model we use has the disadvantage of the slow processing speed because it processes RNN-based time series information. To overcome this, the using of the transformer model, which is widely used in NLP, can be reviewed, and the performance can be also improved through the more detailed hyperparameter tuning. Here's the end of our presentation. Thank you for listening.